Okay, thank you very much for that introduction, Daniel. And I want to thank the conference organisers for allowing me to talk here today. So I want to begin just by sort of looking at brain modelling as a whole. So the brain is inherently this multi-scale object, and this is reflected in the way it's modelled. So sort of at the single cell level, you've got things like Hodgkin-Huxley, which do a good job of modelling sort of single cell dynamics, all the way kind of up to whole brain regions, which are modelled effectively by the neural field type model. So this is what I want to talk a bit about first, the neural field equation. So in this picture of the brain here on the right, this outer sort of spongy region is the cortex, and the neural field, as it is here, does a really good job of modelling the kind of dynamics that are seen in the cortex of the brain. And all it's really saying is that the activity U at some point, if there's no input, it'll decay. But if there is input, then that input is given by summing over all of the connected firing tissue. So really, this is just a kind of description of network architecture inputs to activity in the brain. And it can be written in this kind of succinct form here, where this firing rate is composed with the activity U. And while it does a good job of modeling cortical activity, it falls down when modeling so-called subcortical structures, such as the thalamus. And this is what my work is focused on. And the reason for that really is neural field description doesn't have any notion of kind of intrinsic ionic currents which are at play, which they do play a big role, especially in the thalamus, especially the T-type calcium current, which has been shown to give rise to the so-called post-inhibitory rebound phenomena, which I'll talk a bit more about in a second. But before I do, I just want to draw your attention to some of the rich dynamics that can be seen in thalamocortical models. So Rinzel and co. in the late 90s, in a minimal model of thalamic tissue, they found these sorts of waves which kind of slide or sort of lurch across the domain, and they dubbed them lurching waves. And this is kind of the first time these were seen in models of thalamic tissue. So I mentioned this post-inhibitory rebound phenomena, and now I want to talk about a bit about what this is and sort of how it arises. So in our models, it arises through this mechanism known as a rebound current. So typically in neural tissue, you'd expect some depolarization to result in a firing event, but in tissue endowed with a rebound current, it's kind of the opposite. So you need some sort of initial hyperpolarization. And the way this works mechanistically is with a patch of tissue, which is hyperpolarized, shown down here in this movie, sort of the inactivation of the current is removed, so that when it returns and reaches this rebound threshold, the current's able to activate, at which point there's a large depolarization, which brings that patch of tissue above the firing threshold, at which point signals will start to be sent across the domain, depending on how the tissue is connected to other tissue. And in this way, what we see is that we can get some quite complicated dynamics just from really quite simple initial conditions. Okay, so there's two thresholds at play, a rebound threshold and a firing threshold. So putting this all together, how can we, so what would be an effective model of thalamic tissue? So we know we've got to include some description of rebound, and it's got to be put into a description of including tissue architecture. So what we do is we take the neural field approach, which I spoke a bit about towards the beginning, and instead of composing the firing rate function with the activity U, the neural activity U, we compose it with some function which describes the voltage envelope profile of thalamic tissue. And in that voltage envelope profile, we can include a description of the T-type calcium rebound current, which is given here. So in this way, we get our model. There's 3 currents, and all of this kind of sigmoidal activation functions and the firing rate function are taken to be piecewise linear, so piecewise constant. So these kind of Heaviside type functions. And what we do is we choose a connectivity kernel, which is purely inhibitory. So there's no excitation in our connectivity W. And with this setup, I want to show you some of the patterns that we've seen on the plane. So bearing in mind that this is a purely inhibitory connectivity kernel, we get these kind of sliding hexagons that move across that move across the domain, sort of oscillatory hexagons. And really what's going on here is the rebound phenomena is generating all of these patterns. So in order to kind of understand what's going on here, we're going to take a step back and we're going to consider one of the simplest solutions that we can think of to this model. And that is in one dimension, we're going to consider spatial synchrony. So the kind of thing here that's on the left, where all of space is, where the activity through all of space is kind of behaving in the same way. So taking this spatially independent ansatz for our state variable Z, which includes, the 4 dynamical variables at play here, V, U, R, and H, our space-time model from earlier reduces down to this ODE system, which is piecewise linear. So there are 2 switching manifolds at the 2 thresholds that I mentioned earlier, and at these 2 thresholds, what happens is there's it's kind of a discontinuity or a switch in the vector field. So what we can do is we can solve for the spatially synchronous state for the periodic orbit, in fact, by noting that really away from those switching manifolds, everything's linear, and then patching solutions together at the switching manifolds based on these conditions here. In this way, we're able to construct the periodic orbit, which is shown from 2 perspectives here on the right. And we obtain our analytical results. And then comparing them with our numerical simulation, we see some really good agreement. Okay. So what we're going to do now, we bearing in mind we want to see the kind of patterns that can emerge in the model that we're considering. We're going to do a linear stability analysis of the orbit, and we're going to look at the kind of patterns that can emerge from the instabilities that occur. So taking the orbit and applying a small perturbation, standard theory of periodic orbit stability says that to look at the stability of a periodic orbit, we consider the eigenvalues of this map psi, which takes an orbit over a period. So we want to construct this map and then find its eigenvalues. And for the most part, this is okay, because away from the switching events, our system is linear. But at the switching events, we do need to take care, because those switches induce discontinuities in the perturbation. So we need to make sure that we can effectively map across these discontinuities. And for the most part, in our model, we can do this by following an approach by Muller from the mid-90s, which effectively says that for some local dynamical system, if there's a switch in the vector field, so it's switch in kind of F here, then the perturbations after are related to the perturbations before by this object labeled K, which is called a salutation matrix. Okay, so in this way, we can do kind of 4/5 of the work and take care of all the local terms in the model, which are underlined in blue here. There is one term, though, which arises from the non-locality of the model, which we need to kind of take care of in a different way. And without going through the details, we're able to do this just by considering the original equation for this third variable and linearizing to obtain an entry into the salutation matrix, which contains some notion of space. So it's the Fourier transform of the connectivity, dependent, of course, upon the wave number. So we've got some notion of space in the salutation matrices. And in that way, we're able to construct this map, which takes a perturbation over a period as follows. So it's starting at the beginning of an orbit. We propagate forward using this matrix exponential. We jump into the next region using the salutation matrix, propagate, jump, and so on until we've passed through all our switching manifolds and we've completed the period. In this way, this map size has been constructed. And what we can do now is look at the eigenvalues given a parameter set and a connectivity. So just an example here on the right. For a periodic orbit, if there are any eigenvalues outside the unit disk, then that orbit is going to be unstable. And that's what we see here. There's a big band of wave numbers for which the eigenvalue lambda, the largest eigenvalue is sort of greater than 1. So that's outside the unit disk. And so in this way, we're able to characterize periodic orbit stability. But we can go further because that non-local entry in the salutation matrix only depended on the Fourier transform of the connectivity. We can look at a sort of kernel independent stability. So for a given parameter set, a plot like this will tell us whether an orbit can ever be stable or not. Since the connectivities we use are normalized to 1 and they decay away to 0, the largest eigenvalue will take this excursion, which is being shown by my cursor, and it's going to pass through -1 for this parameter set for any connectivity that we choose. So this is quite a powerful connectivity independent result that we've got here. Okay, so now we're in a position to look at the kind of instabilities that can occur. So on the left, we've got the periodic orbit, the spatially synchronous periodic orbit shown in space-time. This is what we've done all our analysis on, really. And a periodic orbit can go unstable in 3 ways, with an eigenvalue passing through -1, +1, or with a non-zero imaginary part through the unit disk. And the middle and the right plot show 2 of these instances. So we've got an eigenvalue passing through -1 in the middle. In an ODE system, this would correspond to a kind of period doubling type bifurcation. And there's some notion of this in the spatial pattern that we see. So this kind of 2-cycle which has emerged, with every other pattern sort of being kind of offbeat, if you like. But the pattern of interest really is the one on the right, which arises from what would be a Niemark-Zucker type instability for an ODE system. We see these clumps of activity sliding across our domain. And I just want to take your minds back to the pattern that Rinzel and co found earlier on in this talk, those lurching waves. And what we've got here is an instance of lurching waves, these kinds of waves that sort of slide across our domain. And I want to show you what they look like, really. So let me just forward this video a bit. On the right, we've got sort of the spatial profile through time, as shown by a white line here on the left. We see the emergence of sort of an unstable wave number. And at the instability, we see these lurching patterns which kind of slide and move across the domain in a highly non-trivial fashion. So it's currently an open question what we can do to understand these patterns and gain more insight about them, because they've been seen in a few different models of thalamic tissue now. So any sorts of understanding would be definitely welcome. And I realize I'm getting close to my 15 minutes, so I just want to conclude with a few remarks about periodic orbit continuation. So here what we've got is a continuation of the periodic orbit which we've studied. the upper branch is stable and the lower branch is stable, and they come together in a fold of cycles bifurcation, shown by the black dot here. And this sort of leads nicely into the kind of work I've been doing lately, which is looking for ways to continue structures, spatial structures such as this, which are periodic in time, but also have a spatially extended element to them. And that work has been in conjunction with Daniele. And I hope to talk a bit more about that today, but unfortunately, I wasn't able to. So hopefully, in the next few months, fingers crossed, there should be something out there regarding that. And I realize I'm more or less out of time, so I just want to kind of skip to the end and summarize what we've been talking about today. So we've looked at a model of thalamic tissue, kind of the most basic model you can get, which exhibits the post-inhibitory rebound phenomenon, which is seen in real thalamic tissue. And we looked at constructing the periodic orbit solution to that and looking at instability and seeing what kind of patterns arose from doing so. And so with that, I want to thank you all for listening. I want to thank my collaborators. So Stephen Coombs and Rudiger Tool are my supervisors at the University of Nottingham. Yi Ming was a postdoc in our group until a year or so ago. And Daniele, of course, I'm sure everyone here knows who Daniele is. And just a few references here at the bottom for anybody who is interested in looking a bit further into the work that I've spoken about today. So with that, I want to thank you all, and I'm happy to take questions.
Thank you, Sunil. I'll remind people that they can post questions on YouTube, and they'll be relayed to the speakers. Any questions from the audience? I'm handing the microphone to Olivier.
Thank you for the very interesting presentation. I was under the impression that your connectivity function was circularly symmetric. Am I correct? Or
yes, that's correct. Yes.
Okay, so the system is basically one-dimensional because of that. Would it make any sense biologically to consider non-circularly symmetric connectivity functions?
Yeah, so absolutely, it would be, and so that is something that we've been thinking about as a way forward for this work, kind of building on what we've got. And it would be interesting actually to see if that changes the kind of patterns that we get. So, for example, sort of the Niemark-Sacker type instability that I showed, that came when I took, let's say, symmetry away from the kernel. So it would be interesting to see how this would also affect the kind of patterns that we can get. So absolutely, yeah, it would make more sense to do so.
I have another technical question, maybe. You use the Heaviside function of the nonlinearity, and it both simplifies the mathematical analysis and also complicates it because of discontinuity. What do you think? This is my usual question. What would you think of splitting it out into a sigmoid function?
Yeah, so this is a really good question, because we do need to bear in mind that the Heaviside, like you say, it's not the most realistic way to model these sigmoids, right? But the thing is, when we do smooth it out into a sigmoid, we lose the ability to do a lot of this sort of analytical work on the model. So maybe a happy medium would be to consider some sort of piecewise linear function which better approximates a sigmoid than a Heaviside. So that would be one way. You'd still be able to sort of see it would approximate the sigmoid well. It would kind of just increase the amount of bookkeeping you need to do in terms of looking at these discontinuities and mapping perturbations and so on and so forth. What I have found, though, is when comparing kind of purely kind of via sort of numerical exploration by comparing the sort of heavy-side model to the sigmoidal model. There is not much difference in the kind of patterns that we see and in the way activity evolves. So bearing that in mind, it may be worth doing a bit more of an exploration. But I think from what I've seen, the heavy side model does capture quite well the essence of the sigmoidal model, which is good in a way.
Thank you very much.
Thank you very much.
More questions from the audience here or online? I have one. So yesterday, Karina Curto discussed situations of periodic orbits in piecewise linear systems, and this is exactly the setup that you're in. And over there, the question was posed as to what to do with periodic orbits and compute stability of them. In here, it seems to me that you have the saltation matrix that has sorted out this for you. How reliant is this technique on the fact that you have a continuum spatial variable? So could you do just the same with a discretized version of that, in which instead of having an integral, you have a sum at, say, selected nodes? Is that something that you see will work also in that context?
Yes, that will work, because the saltation matrix really it's taking care of what's happening through time, right? And the space, if you like, is kind of only entering. Yeah, the space is only entering the saltation matrix in one of its components, but that's not really the issue. I think I've seen, in fact, perhaps it might have been Steve and Yi Ming, they had a paper out from about 5 years ago, which did look at sort of a network of neurons, which was, like you say, kind of discretized, in which they've done this. So I believe it can be done. Yes.
Thank you very much, Sunil. Any more questions before we move on? If not, let's thank Sunil again.